For this limit, we are trying to find the limit as x goes to infinity of the ratio natural log of x over natural log of 2x plus 1. And so the natural log function, as x goes off to infinity, the function goes off to infinity also. The y values go off to infinity. So when we're looking at this particular limit, we've got natural log of x going off to positive infinity, and then we're also looking there at the natural log of 2x plus 1. Well, if you plug in infinity there, we're talking like 2 times infinity plus 1. We're really just, quote, plugging in infinity again. So we're really looking at natural log of infinity, which we would interpret as infinity, and we have, in fact, the ratio there, infinity over infinity, which allows us to utilize L'Hopital's rule. So we have now the limit as x goes to infinity of the ratio of the derivatives. And so the derivative on the top is the derivative natural log of x, and the derivative on bottom is the derivative natural log of something slightly more complicated than x, but still just a natural log function. So we need to take these derivatives. The top one is a simple memorized derivative, whereas the bottom one needs a chain rule. For the top one, we just have 1 over x, and on the bottom one, it's the natural log of not x, but rather a function of x. So instead of x being at the bottom there, it's 2x plus 1 lands in the bottom, and then we have to pull out the derivative of that inside function. So that would be 2, and rather than writing it out to the side, I'm just going to put it on the top. The derivative of natural log of u is u prime over u, and so that's the form that we have. So we've utilized L'Hopital's rule here, and then typically our next step is to just plug in and see if we can take the limit now. But one thing that I would mention is extremely important, and we see that here in this particular problem, is before you actually try to compute the limit after you've done the derivatives associated with L'Hopital's rule, do some algebra, clean things up before you end up doing any sort of additional plugging in, because sometimes when you do the cleaning up, sometimes things cancel or it makes it easier to plug in to begin with. So we've got a fraction divided by a fraction. So really we've got a fraction multiplied by the reciprocal of the bottom. So we are looking at the 1 over x times 2 times x plus 1 over 2. And so putting that all together, notice how I've kept on with this limit for each case because I haven't actually taken the limit yet. I've got 2x plus 1 on top and 2x on the bottom when you do the multiplication on the bottom. So with this function, now we no longer have any natural logs at all. This is a rational function, and rational functions, we could take these limits. We could use algebra, or we could use the fact that we learned the leading term, the leading coefficient. Well, really the leading term on the top divided by the leading term on the bottom is really what dominates. But now that we have L'Hopital's rule at our disposal, we don't even have to remember that sort of special case when we were talking about x going to infinity, because see, what's really happening here is on the top we've got this line with positive slope, so as x goes to infinity, so does the y value, and again we've got the line there with a positive slope too, so on the bottom it also goes off to infinity, so we still have an infinity over infinity situation. I showed you the indeterminate, and so really we could use L'Hopital's rule again and not have to remember anything particularly special. And definitely not different than what we've already been doing in this particular problem. So for L'Hopital's rule, we take the ratio of the derivatives, and perhaps we may want to rethink if derivatives were very difficult, but derivatives of these lines are super easy. So writing these steps in here doesn't take too much. The derivative of the top one is 2. The derivative of the bottom one is 2. And so we're really looking at the limit as x goes to infinity of the constant function 1. That constant function is just a horizontal line, and so that limit then is going to just be that y value of 1 there. And so that completes our limit, but realize the thing that we learned from this example was the importance of, after applying L'Hopital's rule, to do any sort of algebra cleanup and manipulations that we can first before we reassess our situation. So that was the take-home message for this example.